Hi, and thanks for tuning into the second episode of the Galileo interviews. I'm honoured to have had the opportunity to speak to Dr. Rushen Patel. Having studied aerospace engineering at Cambridge and receiving his PhD in control theory at Imperial College, he has applied his skill set in problem solving using data science and machine learning to a vast variety of different sectors. From Formula One to using AI to revolutionise student loans. I really enjoyed exploring his journey with him, as well as hearing his advice for up-and-coming problem solvers and learning more about AI. Enjoy! As an engineer, what's the most interesting problem you've ever worked on?
Oh, there's probably a few that I quite enjoyed working on. I think, probably going to my Formula One days, actually, Red Bull racing. I think overall, that was a really interesting area to work in. I worked on a problem around basically optimizing the race car using simulation. So we built a tool for performance engineers to understand what the best parameters were for the car setup at race time. And so ahead of time, they could simulate the car basically racing around the track using computation only, understand the sensitivity of different parameters like tire pressure, flap angles, etc., to the car speed through corners, and they could use that then to kind of optimize those parameters before the race itself. So that was very cool in terms of the context. So that was really good. And I think I enjoyed that one actually because it incorporated quite a few different sort of aspects of what I'd learned in the past. So a lot on simulation and modeling, but also a lot of optimal control, which is what I studied for my PhD, which is sort of techniques for optimizing systems. That was really fun.
So just backtracking there for a second, talking about your education, your background, what interested you about physics and engineering to begin with when you were young, and what motivated you to then go and study it at Cambridge?
So I think just wanting to know how things work. So I've always wanted to know how things work really from when I was young. So, just pulling things apart. I think physicists and engineers probably always say this, but just tinkering with stuff, breaking stuff, seeing how it works under the hood, and not even just man-made systems, right? But the world around you. How does it work? How does the climate work? How do the planets work, etc. So, probably natural curiosity for how things work is what sort of drove me towards sciences probably more than any other area. And then within that, I was probably erring more between physics and sort of engineering. I was erring more towards trying to impact, trying to build things that impact how things work or how the world works, which is why I probably went more for engineering than a kind of pure subject. Maths or physics. So I was like, okay, I'm going to take those concepts, the learnings, and now how do I actually implement those in systems that can impact the world?
Talking about the concepts and learning, what do you think the greatest thing you learned was whilst you were at Cambridge?
Probably just to learn how to learn. So there's probably not one, concept or thing that you learn that is going to, change your life necessarily. You learn lots of things, right? At university, you're going to learn theoretical things. You're going to learn practical things, potentially how to program, all those kind of skill sets like that. But what you really learn when you leave school, at school, you get a lot of help. And, particularly at good schools as well, you get, they teach you really well, right? And they teach you what to learn, and they set the pace. And of course, they try and stretch you. when you get to university, you're pretty much left to your own devices, right? So it's much more, you've got much more autonomy, and the people that thrive, I think, are those that sort of just take on the ability to learn for themselves without any external motivation. Learning how to, spending time on difficult concepts, trying to understand things that you might not necessarily understand to start off with, that persistence, just being able to sort of get your head down and work really hard, I think, on certain things. You'll find that post university, then you might forget. I've forgotten from school. I've forgotten probably 99%. From university, probably at least 80%, because I don't use it day to day. But the ability to kind of go into books, read stuff, try and remember how things work, pick up new things quickly. I think that is really key, and that's why actually it doesn't matter so much what you study necessarily, but it's how you study. I think that becomes really important.
A very universal life skill.
Yeah, exactly.
Yeah. So what was the transition like from going from that academic study and research into industry? What did you have to learn for that?
It is quite different. So a PhD is obviously very academic. You're in quite an environment where you're surrounded by people really that think very similar to you, right? Everyone's sort of quite scientific, quite quite into the work they're doing. The kind of delivery of results is different as well, right? The time frames, you have much more time to explore things, to go off on tangents or different branches of research which you're interested in. Once you get to industry, in the end, you have to deliver results. And the approach is probably not the most important thing. You start at what are you trying to deliver, what is a value you can add, and you work backwards to, okay, what is the best tools, solutions to deliver that value. So it's going from a research mindset to a commercial mindset. So and in that you then have to, of course, work with a huge range of stakeholders, which who aren't necessarily scientific, right? They might be commercial, business people, finance people, marketing people, a huge range of people, and they don't. Some of them have science and maths backgrounds. Some of them don't, and being able to, anything you do on a research or engineering side, being able to translate that to people that are coming from a non-technical background is very important. But yeah, it's definitely a big change.
Was it quite difficult to learn to explain some obviously quite high-level concepts to people from a non-technical background in the beginning, to try and explain what you're doing?
Yeah, and some people naturally are good at this. I think it takes time. For me, it took a bit of time. So when you go to a PhD research conference, you can be really mathematical, right? And that's the expectation. And it's almost, the expectation is that no one will, or half the people won't understand what you're talking about. Whereas that's not going to work in industry. So it's really, that part is really practice, actually. You just start doing it, you start to understand, as long as you're willing to take on the feedback, you start to understand, okay, what is the level I should be pitching technical concepts at? And really, even today as data scientists, we keep a lot of our conversations very high level with stakeholders, because that's actually the level they care about, really, and the level that impacts them. But yeah, it takes a lot of practice to get to that. And you see it. I see it when in my team now, when people join from university, everyone's really keen to talk about the cool sort of models that they're building. Get really into the depths of detail, because that's where you're showing that you're worth your paycheck. But the stakeholders, etc., that they're presenting to, unless it's to a scientific audience, might not be that interested in that. So there's always a bit of coaching around that. But yeah, it takes practice.
How do you go about solving problems then in industry? Do you approach problems in a certain way usually?
Yeah, so I think it's a bit different between potentially engineering and data science, where I work now. But if I start at data science, because we have quite a clear path actually to how we solve a problem. So we understand the business problem first and foremost, right? So we're always driven in commercial data science, if you like, rather than research data science. We're always driven by the business problem. So we would have an inkling that there's a problem, in a business, in a problem space that data science might impact, right? And the business who we might deliver that solution into, the kind of what we call SMEs, the domain experts, basically, they will also have an inkling that, okay, data science can help them. But we'd start with that high level, okay, what is the problem? And we would do a kind of discovery phase. So we'd spend 2 or 3 intensive weeks working with all the stakeholders involved in that problem space around, what is their current method of solving that problem? Because usually there's something already in place, right? Why is that not sufficient? Where could data science potentially help? Do we even have the data to help there? So we go through this whole process before we've done any, sort of scientific stuff, any modeling, any data science. We go through the process of understanding the problem and understanding the potential value solving that problem could deliver. Once we get to that, then we say, okay, we've got the value now. We understand the problem space. We think the data's there. Now, is it worth us solving this? Because it might take 3 months. Well, actually, it will usually take at least 6 months and probably over a year, right, of resource for a data science problem. So we then have to prioritize. So we might do discovery on a bunch of stuff, bunch of different problem spaces, but then really focus in on the ones where we think, okay, either the value is good or what we call the time to value. So how long it would take to start delivering value to and profit to the business is short. If those two look good, then we might start the actual sort of modeling, etc.
Okay, so then how about in engineering? How did you go about?
Yeah, and engineering, the problems are better defined actually. Usually, the problem exists, and everyone knows about it. So, both in oil and gas, when I worked in oil and gas and F1 as well, we would, there would be an acknowledgement. So management would already sort of have an idea of what they're trying to build, right? So in oil and gas, I worked on drilling automation, so automation systems for drilling oil wells. We know it's very clear that the industry, it's a really manual process, right? So it only makes sense to automate it in some way or as far as possible. And then the question is, okay, how do you go about doing that? In F1, it was clear that we want to improve the performance of the car, and that simulation was going to be the way to do that. So then it's going straight into okay, how do we actually build out that solution? So the problem spaces are defined, I think, in engineering, much more so than in data science. And we, as engineers, we go in and we just start working on those almost immediately. So you could almost be hired in to work on a particular problem. In data science, that's less the case, and partly because data science is also quite a new subject for industry. So people are still working out exactly how to deploy it.
Okay, so going back to data science, I know that you spent some time with Vivacity Labs using reinforcement learning to optimize traffic flow.
Mm-hmm.
Could you, for the audience, briefly explain what reinforcement learning is, how it works, and how you applied it to this project?
Yeah, absolutely. So reinforcement learning is probably the closest sort of form of machine learning to real artificial intelligence as we think about it. The concept is actually super simple. So if you're and it's basically mimics how we as humans learn and how children learn. So um, a child, if they do something good, you tend to give them a reward, right? So we give them, chocolate or whatever it is. Uh, that makes them happy. It releases endorphins in their brain, etc. And then they'll recreate that good behavior, right? That good action. And similarly, if they do something bad, there's a penalty, right? You either tell them off, etc., etc. So that's exactly what we do in reinforcement learning. So you have a computer, an agent, which is just a computer program running, and we let it do stuff. And we let it do stuff usually in simulation first, right? So you don't let a computer run wild with traffic systems in real world, right?
Yeah,
So
that would be interesting.
yeah, exactly. That's going to end badly. So the first thing you need is a really good simulation of your environment. If you don't have a simulation that is of high enough fidelity or realistic enough, then you can't really use reinforcement learning. It's just not going to work. And that's why it's not used everywhere, basically. But if you have a good simulation, and in traffic problems, we have what we call micro sims, so we can simulate traffic actually to a reasonable degree of accuracy. The flow of cars, traffic lights, or how everything's laid out. So we can do that, and we can have a simulation where we have cars sort of driving around, a different driver behavior, etc., and we can stick an agent as a acting as that traffic light and say, okay, but you've got some options, right? You've got some actions that you can take. So you can do green, you can change this to green, you can change this to red. There are some actions, and there's not an infinite number of actions. There's a set number, 4 or 5 actions typically a traffic light can do. They can show green, to one direction, and then green to the other direction, etc. And then pedestrians. So you've got these actions, and so we just say to this agent, right, you go off in the simulation, and you start, and at the beginning it actually randomly starts taking actions, right? And we have a metric for the reward which we're trying to optimize for. And for traffic, it's usually things like journey time, or waiting time. So we're trying to minimize the waiting time on average for all the cars in that simulation. So it does a bunch of random stuff, and it starts to get reward. So if it makes actions that penalize the traffic over, that increase waiting times, that penalizes the agent. The agent gets a penalty signal. If it takes actions that reduce the waiting time, it gets a reward. And so from the inputs, the environmental inputs that we give it can decide, okay, given this set of inputs, in the past, I've got a reward for taking this action, or I've got a penalty for taking this. Conversely, I've got a penalty for taking this action. So over time, it starts off and it's doing horrible things. Over time, it starts to learn what actions give it the most reward, and yeah, we effectively, that's how we train a reinforcement learning agent. So we let it learn in simulation what the kind of what we call the optimal policy is. So for any given input state, for inputs it receives, what would be the optimal action for it to take. And for traffic lights, the inputs actually come from cameras. So so at Vivacity, we set up cameras around a junction. And there's processing, so there's computer vision, so that detects cars. It then identifies how long the queues are on each of the arms of the junction. It identifies if there's any pedestrians, etc., cyclists, buses, trucks, all these things. So yeah, this whole rich data set of inputs that we then feed into the agent, which it's seen before through the simulation, that we then we can feed in and basically once it's trained, it will just take those inputs and then kind of enact the optimal action every time. And then we let it loose in the real world and see how it does.
Is this now operational in certain areas now then?
Yeah, so it was operational. It was that project I was working on was actually a first of its kind, deploying reinforcement learning in a real world safety critical context. So there's a lot of safeguards we put in, just so we're not scaring. I don't want to scare anyone. We don't.
Let's avoid lawsuits too.
Yeah, so we have a lot of we basically have certain things that can't happen, right, for safety.
Yeah.
But yeah, we deployed it in Manchester as a test bed. That project actually has just about finished quite recently. It showed you could reduce waiting times up to 40%, if I remember rightly. So a huge amount, right? So, and we did, and in that project, they just deployed it across 5 junctions. So we simultaneously train 5 agents on a kind of key set of intersections. It's been really successful. So they're rolling it out. Actually, I believe they're doing a test in Cambridge now as well for that. So it was a 3-year project, but we built the whole thing from scratch really. But yeah, it's already sort of now just about starting to take off potentially as a real product that you can sell to councils and governments who run the different traffic systems across the country.
It's awesome. So I saw that you published an article on a model predictive control framework to guide policy decisions on social distancing on LinkedIn. Can you explain how these sort of models work and how beneficial it would be to use systems like this to guide decision making, particularly right now? Yeah,
I'm good. You've done your research here, so kudos to you for that. That was actually, and I can probably link that into the reinforcement learning. So in reinforcement learning, we don't have a model for the world, right? Implicitly, the agent builds its understanding of the world. We just let it, take a bunch of inputs. In model predictive control, we're solving similar types of problems. So these are control problems, right? Of what action should we take to get an outcome that we want, and it can be in a system like a traffic system, or it can be government policy making, right, or decision making within a business. So with model predictive control, the sort of name gives it away. You actually have a model of what you expect to happen. So in the COVID-19 case, you can model how disease spreads over time, and you can link that with the inputs, the decision points that you have. So in a pandemic, you essentially have a social distancing decision action that you can take. You can have complete lockdown, or you can have just schools locked down, or you can have just wearing masks. There's different levels. There's a kind of continuum of levels of social distancing. And so in a similar sort of way to how we work with any control problem, you can try and work out, given an objective, which is to try and minimize the number of people going to hospital, usually below a certain threshold, which is your hospital capacity. What is the level at any given point, given I've got X number of cases and the rate of increase or decrease is X, at any given point, what is the social distancing parameter I should be applying to ensure that I stay below that constraint, right? The hospital bed constraint, or whatever it may be. So that's where I try to apply model predictive control in that setting, and it actually works quite well. I'm not sure if the government ever used it, given how much we sort of bounced in and out of different lockdown. You can apply it to that, right? I think that the challenge with COVID-19 is obviously how good is the model really. There was a lot of uncertainty actually in what we call the R numbers, so the rate of the rate of infection. But in principle, yeah, you can, that kind of process of trying to model what will happen in the future given different inputs at different points. If you can model that, then you have the option of using something like optimal control, model predictive control, or even, if you can simulate, you can use reinforcement learning. So they're all decision-making tools, actually. They were built for systems, for like controlling complex systems, actually originally to basically control missiles. That's where control theory kind of became, effectively for defense. It was researched heavily in the 50s and 60s for defense purposes, but obviously then used for everything, right? So aircraft control, spacecraft, and but started predominantly in that engineering space. But you can then start to apply it to economic, social problems, biological systems as well. Yeah.
So what's been your favorite startup to work on, and why?
I think so. Vivacity is definitely up there, I think, with has been one of my favorites, because I think we were doing something so novel there, and basically deploying this sort of AI in the real world as a first of a kind use case was very cool. The only other one I'll mention is one I'm sort of advising at the moment called Prograd, and they're doing something really interesting around financial inclusion for education. It's a company that are looking to. So when you go to university, you can take a student loan, but not everyone. Not everyone can afford all their expenses just with a student loan, and then some people fall outside the sort of student loan umbrella for various reasons. They're either doing master's courses or mature students, etc. And they don't really have very many financing options apart from going to high interest sort of lenders. So what Prograd are trying to do is build a capability to score those types of people. So people, what we call with thin credit files. So because they haven't had necessarily a lot of loans in the past, they don't have a credit score, basically. And something, you probably would never hear, if you're young, you won't have heard about it, until you start start earning and start taking credit and start getting loans for mortgages and all that kind of stuff. Because they haven't had earnings in the past, they can't necessarily get loans from banks, normal banks, because banks can't assess the risk. But with sort of Prograd's technology, where what they try and do is predict how you'll perform in the future. So if you're taking a course from a certain university, they will say, okay, we predict you can earn X amount, upon graduation. And banks can then use that forward prediction in there to assess how much they want to lend someone. So it's quite cool.
That's really cool.
Yeah, it's quite nice. Yeah, and the idea, really, the mission is to try and help people get an education where, if they're not, or a further education, I should say, if they want to, but are struggling financially, to do that.
That's awesome. Okay, so if you could choose to work on anything else in the future, what would it be?
Right, I'm going to have to think about this one. So,
yeah, it's a big question.
That is a big question. One thing I do actually want to go back to at some point is reinforcement learning and optimal control, which sounds weird because I've done a bit of it, but I think the potential for those kind of technologies to impact the world, and you see a bit of it if you've ever heard of the company called DeepMind, who they were bought by Google a couple of years back, but they've made some huge breakthrough. So they're a reinforcement learning company, probably the most famous. They built AlphaGo and these kind of agents that can beat anyone at Alpha and various other games actually. But they also did something quite recent called AlphaFold, where they solved the protein folding problem, and that in itself is an incredible achievement, right? So people have been trying to solve this for decades, basically, and it's a really complex problem, right? There's the number of combinations of it's so large that getting sensible solutions is really difficult, which is why generating protein new structures for medical use, etc., has been so difficult. Using reinforcement learning, there's effectively solved that problem, and there's probably a huge number of other problems like that where you can have a huge impact. It's not AI where people are sort of robots are walking around in the world interacting with people, but it's really cool that you can that will help longer term with medical development, medicine development. That will really help people. And I think there's still areas across biology, manufacturing, energy, another domain where obviously we need to make a huge strides technologically to deal with climate change, where I think the kind of things that I like working in, optimal control, reinforcement learning, can have an impact. So when I'll go back there at some point, I think. I'm not exactly sure when. But I really enjoy working on those problems.
That sounds really exciting, and there do seem to be just countless different avenues for potential really promising applications. So can I ask you just a couple general questions about science?
Of course.
At the end. So, which idea in the history of science do you believe was the most revolutionary?
Ooh, okay. Right. Now I'm going to have to think. There's been quite I guess there's been a few, right? Obviously, the whole industrialization. There's probably a couple you can point to that have made huge impacts. Electrification, I think, is a huge one. Changed just the way people work and live completely. So there's certain technologies which are what I'd call general purpose technologies, which impact everything and everyone's lives, right? Electricity was probably one of them. Probably the invention of the jet engine is another one that led to a lot of sort of acceleration of globalization. There's probably medical ones, but I won't go into those in too much. And more recently, the invention and continuing development of computer hardware, actually, more than software. So AI is all based on the fact that hardware has got so much better over the last couple of decades. So the silicon chips being more Moore's law, being more and more powerful. And the next one, I'm not one for making, well, actually I probably am because I'm a data scientist, so for making predictions, but quantum computing, I think, could really have huge impact in the future.
Do you think that could have a really significant impact on AI and machine learning?
Yeah, absolutely. Because the biggest machine learning model that I've read about so far is GPT. It's called GPT-3. It was trained on a supercomputer. I think Microsoft's supercomputers. I can't remember exactly, but something like 130 billion parameters that you have to tune for that model, right? It's essentially a whole bunch of neural networks, which each there are millions of weights, and there's actually billions of weights in those huge models that need to be tuned as you train it, right? So if you can find the process, and that's very that takes a huge amount of hardware, and it's very time consuming, which means for your average, your average company, etc., then they might be able to use the model once it's been trained, but they wouldn't be able to train their own at that scale. But with quantum computing, you move away from this, this notion of binary, right? 1 and 0. So, and it allows you, although it's very restricted at the moment, it then allows you to process a lot more data, or a lot more, I should say, computations quicker. And so I think it will have an impact on machine learning, also just on general optimization. So there are problems that we find very difficult to solve at the moment. And as strange as it may sound, like routing is a really difficult problem. It's what we call NP hard. It's basically, there's no like perfect solution for if you have many like nodes and you're trying to find the optimal route, the shortest path between a whole bunch of different nodes that you have to get to. So you can think of a delivery driver from Amazon, right? Those problems are really hard to solve and take a lot of time. Whereas with quantum computing, you can start to solve those much quicker, which then opens up much larger optimization problems. So yeah, it's definitely an exciting space.
Yeah, definitely. So just to finish off, because I think we're probably out of time, what if you could give one piece of advice to someone sort of around my age, 17, 18, looking to go into physics or engineering, what would it be?
Yeah, so I think work hard is going to be a good one. But just take the opportunities to learn where you can. Whatever. There are lots. There's loads of universities, obviously, that teach physics and engineering and any of the sciences, and loads of them are very good, right? And people get hung up about what university you go to, what exact course you study, what exact mark you get. But actually, a few years outside university, unless you're staying in research and in the academic setting, no one's really going to be looking at that kind of stuff. Actually, they're going to be looking at what you've done in the immediate past. So when you do, just whatever you end up studying and whichever university you end up going to, take all the opportunities that you can to learn, and not necessarily just to focus on the theoretical aspects, which every course will cover, but the aspects where you can build, particularly for your future career, build some of the other skills that you need. So definitely learn how to program if you get the chance, at least just to start learning that, and also soft skills, how to present, how to sort of explain difficult concepts to people. All of that's really helpful when you get out of academia again.
Thank you so much for doing this with me today. It was really interesting talking with you, and I'm sure a lot of people are going to enjoy watching this.
Well, thanks, Casper. Thanks for inviting me along, and good luck with your own studies as well.
Thank you. Thank you. Yeah, this was really cool. So there you have it. Thanks for watching the second episode of the Galileo interviews. I hope you found the discussion as interesting as I did. There will be plenty more guests, so don't forget to like and subscribe below and share with your friends.